Here we are again, and this time we're going to start talking about basic solutions. This one should be pretty quick, so let's get straight into it. As we were talking about in the previous video when we were talking about defining acids as proton donors and bases as proton acceptors, is the other side of that. So when we talked about it being an acidic solution, we talked about it being relative to the concentration of H+, or the other way of saying this, H3O+, because remember we can use the terms H+ and H3O+ interchangeably, because anytime we have excess H+, that will find itself a water molecule and form H3O+. So for an acidic solution, we're talking about a solution where we have more H+ than OH-. So for a basic solution, we're talking about having more OH- relative to the H+ concentration. It doesn't mean that the concentration of each one is 0. It just means that we have more OH- in solution than H+, because they can constantly be changing between the two. So if we dissolve something like sodium hydroxide into water, it ionizes to give us Na+ and OH-. Straight away, we can see that by doing that, we now have a free OH- ion. Its protons, it's free to move and sop up any H+ that's in solution, or to rip a proton off a water molecule, forming another OH- ion and H2O. But essentially what we're doing is we're shifting this balance, or what we call this is an equilibrium. And we'll come to talk about equilibrium later on this year. But essentially equilibrium is a balanced position. We're looking back at those seesaws and we're moving it now onto the side of having more OH-. A basic solution contains more OH- than H3O+ ions. That's all it is. And a base is a substance that is able to accept a H+ ion. So in the case of OH-, if it accepted a H+ ion, it would form H2O. So in basic solutions, this is the same old situation that we've got here. We have a situation where we have the water, ionized water, self-ionized water, where we have a mixture of H3O+ and OH-, and we add sodium hydroxide into it. And what's going to happen is the OH- now frees up, dissociates from the sodium, giving us sodium+ and OH-. That will rip one of the protons off what was a H3O+, leaving H2O. And what we've done now is this now forms a H2O molecule. And we've decreased the amount of H3O+ relative in solution, because we now have 4 water molecules, well, before we had 2 water molecules and a H3O+ molecule, and then this guy here, which is still an OH-. So the H3O+ has been removed, and then the OH- is left behind, and this is what we call an alkali solution, or a basic solution. So in a basic solution, the OH- concentration is greater than the H3O+, and that's what changes its pH to something above 7. So if we look at the properties of bases, they're different to what they are with acids. And all bases can be things like metal oxides. So this could be something like magnesium oxide that we made in by burning magnesium, resin, and oxygen in semester 1. It could be metal hydroxides. So this could be potassium hydroxide, might be lithium hydroxide, or sodium hydroxide. It can be metal carbonates, so something like sodium carbonate, Na2CO3, metal hydrogen carbonates, which is bicarb, NaHCO3, or amines, and this is where we get into things like ammonia. So anything that has that nitrogen atom on it with a lone pair, because amines can form dative bonds to the H+, forming, if we form a dative bond, we get that NH4 plus ammonium ion. Okay, so what you may notice about these is metal hydroxides dissolve to give us OH-. Magnesium oxide will actually dissolve and react in water and give us OH-, because it's a alkali metal, alkali earth metal. Alkali meaning it turns into a base when it reacts with water. Metal carbonates, these break down, we get CO3, and you may remember that when these react with an acid, we get salt plus water plus CO2 gas. Okay, and then same with our hydrogen carbonates. Amines can accept a proton by forming an NH4 plus or NH3 plus if it started out as NH2. These have differing effects on indicators than what acids do. So whereas an acid with universal indicator below 7, we go into the red, orange and reds. When we're doing a base, we go up into the blues and purples. And then neutral is usually around 7 and it's green. Bases will react with acids in neutralization reactions. Hopefully you remember that that is when we add an acid plus a base, we get a salt plus water. So that's known as a neutralization reaction, which is an exothermic reaction. And aqueous solutions of bases are also electrolytes because they have free-moving charged particles. The ions dissociate. They're an aqueous solution of ions, which means that they can carry a charge. They also, when they are an aqueous solution, we refer to that as an alkali solution. It's a special name that we have for aqueous solutions of bases. And they taste bitter. So where acids tasted sour, bases taste a bit bitter. So if we have a look, one way to think about bases also is that if this is all the bases, this circle represents all the bases. So we've got copper oxide, magnesium oxide, calcium oxide, sodium hydroxide, all the different things that we listed up here. Not all of these will form alkalis. Alkalis are soluble bases that give off OH minus, so sodium hydroxide and potassium hydroxide would be our alkalis, and that when we dissolve them, they form OH minus in solution. The other ones need to go through a couple of steps, so they're not necessarily known as alkalis, and most of them aren't actually soluble. These are the common bases that we have to know. So same as there was common acids we have to know, these are common bases we have to know. Any of our metal oxides, so calcium oxide, copper oxide, sodium hydroxide, lithium hydroxide, these are strong bases. Calcium hydroxide, you will notice that this is forms one OH minus, one OH minus. This one will give off two OH minus when it reacts. Barium hydroxide will give off 2 OH minus when it reacts, and ammonia can only accept one proton as well. So there are a couple of safety considerations that we need to talk about when we're dealing with acids and bases. We always have to wear a lab coat, safety glasses. Make sure we label our bottles and containers because most acids and bases, when we just pour them into a beaker, look the same. They're going to be clear, colorless liquids with no distinct odor. They're going to look exactly like water, but we need to be very careful when we're dealing with them because they do have safety considerations because they're all corrosive. Whether an acid or a base, they're all corrosive. They have this safety symbol here with the little hole being burnt into the hand and into the surface, meaning that they're corrosive and will cause burns. When we dilute acids, okay, we have to add the acid to the water. So have a go, pause the video, think about why that might be. It's relevant to the topic we just finished, and then set the video again once you've written down your answer. Right, hopefully you had a go and you just didn't leave the video run and you had to think about this. We add acids to water because the dissociation of an acid is an exothermic reaction. So when we add the acid to the water, it's going to give off a large amount of energy. Because the water has a high specific heat capacity, it's able to actually absorb that energy without changing temperature too much. If we were to add the water to the acid specific heat capacity is much lower. So the acid can actually generate enough heat that it might start to boil and it might spit, which then makes it unsafe to deal with because we have this spitting, boiling acid, which can only end badly. Okay, so these are the things that we need to consider when we're dealing with acids and bases. So that's pretty much it for the properties of our acids and our bases in terms of a base being a solution that has a higher concentration of OH minus, an acid being a solution that has a higher concentration of H3O+. Next up, we're going to define both of these according to the Bronsted-Lowry theory, which is the theory we need to know for SLIB.